This is Jack Jackson with part 5 of our series of lectures on probability. This one is on conditional probability. We're going to start by looking at what we call a two-way contingency table. In this case, we're going to use for this example a comic book collection owned by this guy named John. And his comics come in two publishers, DC, denoted by D, and Marvel, denoted by M. And in three conditions, good, fine, and near mint, which we're going to denote by G, F, and N. So the first thing we want to do is compute some basic probabilities. Probability of D, probability of M, probability of G, etc. So please take a few minutes and compute all of these probabilities and then come back. Please press pause now. Well, we're back. One of the things that you probably had to do whenever you were figuring these out was to compute totals. And here we see that we can add up the total across each row to find the total number of DC comics, 1,088, and the total number of Marvel comics, 870. And then the total down each column to find the total number of good, fine, and near mint. So for example, the 211 represents the number that are both good and DC. But if you add up all three of the numbers, 211 plus 557 plus 320, you get 1088, which is the total DC. Now, if you still haven't figured it out, please go ahead and figure out the rest of these probabilities, and these numbers should make things a little bit easier for you. Please press pause now. Well, here we go. Here are the answers to this. Hopefully these agree with what you came up with. For example, the probability of a DC comic is 1088 over 1958. That is the probability that if we choose one comic from random from this entire collection of comics, what's the probability that that will be a DC comic? And it's just the relative frequency of DC comics. Similarly, the probability of a Marvel comic is 870 over 1958, or approximately 44.43%. In a similar manner, we can figure out the good, fine, and near mint probabilities. When we do the probability of good and DC, that's G intersect D, then we want to just take the 211, but still dividing by the total 1958, because we're choosing the comic randomly from the entire collection of 1,958 comics. That's about 10.78%. When we get down to the OR categories, like probability F union M, probability of fine or Marvel, then what we're doing is we're adding up all the ones that fall in that category. Notice that's 557 plus 133 plus 235 plus 502 for a total of 1,427 over for the sample for the event size over the sample space of 1958. So that fraction reduces to about 72.88%. We could have also found that some slightly different way, since we already have some partial sums. We could take the fine number of 792 and add the 133 plus 502. Or we could have taken, probably the easiest way, we've already added up the three red numbers there for the Marvel total of 870, and all we have to do is add on to that the 557 that are fine but DCs. Notice, however, you cannot add just the 792 and the 870, because that would count the 235 comics that were Marvel and fine twice. So be sure that you count all that are fine and all of them that are Marvel together, but don't count anything twice. Similar manner, we found the other probabilities there. If you need to, press pause and take a minute to look over all these and check them with your figures. When you're satisfied with that, let's go on to the next slide. This slide here shows the probabilities of each of the categories in the table. So for example, the 211 over 1,958 is the probability of good and DC. The 870 over 1958 is the probability of Marvel. The 822 over 1958 is the probability that it's a near mint, etc. And these numbers are given both in fraction, non-reduced form, and a rounded off percentage form. Now, let's get into something slightly new here, and this is where we're going to start introducing the idea of conditional probability. Now, what we want to do here is, suppose that we have chosen a comic at random from the collection, but we know some extra information. We now know that it's a Marvel comic, and we want to know the probability that it's a near mint. Okay, if we just say what's the probability that this comic is near mint, and we didn't know any other information, we would say that's 822 over 1958. But if we say, oh, somebody picks the comic and says, oh, this is a Marvel comic, now we know some more information. Okay, now what's the probability that it's a near mint? Or in other words, this is basically the same thing as saying we're choosing a comic only from the Marvels and seeing what's the probability it's near mint. This is called the probability of n given m, denoted in p parentheses n, vertical line m, parentheses, probability of n given m, probability of near mint given the Marvel. What is probability of n given m in this case? Go ahead and figure that out now. Press pause now. Well, we see that this value is found by really just ignoring everything except for the Marvel line in the table. So we take this row containing the Marvel comics, and now the sample space has basically been reduced to the 870 Marvel comics because we have that information that we know it's Marvel. So we're choosing out of the 870, we want to see how many of those would be near mint, which is 502. So 502 over 870 is the probability. That's about 57.70%. So that's the probability of near mint given Marvel. Okay, let's reverse it. What's the probability of Marvel given that it's near mint? Press pause now. Well, what did you come up with for this? Let's take a look. So when we're doing near mint given Marvel, we only considered the Marvels at line. When we do Marvel given near mint, what will we do? Well, we'll only consider the near mint column. And so this is still 502 that are both Marvel and near mint, but we're doing out of a total of 802 this time. That reduces to 251 over 411, or about 61.07%. So if we know it's near mint, we only consider the comics that are near mint, which are given in that particular column. This is conditional probability. Notice, for example, that the probability of Marvel given near mint and the probability of near mint given Marvel had the same numerator but different denominators in the fraction form, and of course hence different probabilities. So how do we figure this out? So if we're doing basic probability for a finite sample space, they're applied when we're choosing from the entire sample space or the full collection. No additional information is provided, and the relative frequency is the probability. The probability of an event is the size of the event divided by the size of the sample space. So the denominator is the size of the entire sample space. For example, here, our entire collection of 1,958 comics. Conditional probability for a finite sample space applies when we're choosing from a subset of the entire sample space or subcollection. In other words, we're given additional information that the item is from that subset. So the relative frequency of the intersection as a part of the given set is the probability of A given B. So probability of A given B is the size of the intersection of A and B divided by the size of B. Notice that we're doing the overlap of the two sets for the numerator, the size of that, and the size of B, the size of the given event, goes on the bottom. So the one that's given goes on the denominator. So using these definitions now, let's find out these particular probabilities. This is the probability of G given M, probability of M given G, probability of N given M, and so forth. Please compute these now. Please press pause now. Okay, here's what I get for the answers here. I'll go over a couple of these and then you can press pause if you need to review all these. So for example, to do probability of G given M, it's the size of the intersection of G given M over the size of M. So we're basically looking at the first row there, the Marvel row, and the size of the intersection, good and Marvel, is 133, and out of the Marvels of 870. So the probability that we select a good one, given that it's a Marvel, is 133 over 870, or about 15.29%. In a similar way, you figure out the rest of these. Let's go ahead and look at the answers you came up with, check them against all of these. We'll press pause and then resume in a minute. Press pause now. Okay, we're back. Hopefully you've checked all those probabilities. Now, when we get to a finite sample space, which is what we have here, we can look at the probability of A given B was the size of the intersection of A and B divided by the size of B. Of course, if we wanted to, we could divide the numerator and denominator by the size of the sample space. And notice then that the numerator is just the probability of A intersect B, and the denominator is the probability of B. This is going to be our general definition of the conditional probability of A given B, and this will apply even when we don't have a finite sample space. So the probability of A given B is defined to be the probability of A intersect B divided by the probability of B. So notice that the definition of conditional probability gives us two different expressions for the probability of the intersection of two events. So over here on the left we see the probability of A given B is probability of A intersect B divided by probability of B. Multiply both sides by probability of B and we get the probability of A intersect B is probability of B times the probability of A given B. On the other hand, on the right here we see that probability of B given A is the probability of the intersection divided by the probability of A. Multiply both sides by the probability of A, we see that probability of A intersect B is probability of A times the probability of B given A. So we notice that there are actually two different expressions here for probability of A intersect B. We can take the probability of B times the probability of A given B, or the probability of A times the probability of B given A. And this allows us sometimes to find an interplay between these two to help us out.